Welcome to the Crazy Hat Chemist. So another video here on Thermochemistry Part 2. So let's get moving. Bam! So today we are talking about the shift from non-spontaneous to spontaneous. In fact, this video just covers this concept. Although I did cover this concept from non-spontaneous to spontaneous and spontaneous to non-spontaneous in some previous videos within this unit. And I graphically displayed both of them. Okay, one with a positive slope and one with a negative slope. So make sure that you take a look at those videos. They're rather lengthy, but they're very important to understand conceptually as well, and therefore that's why I graphed them for you. But this is just a separate problem dealing with the non-spontaneous to spontaneous shift, figuring out what that temperature value is, okay? And an understanding of Gibbs Free Energy. So if that video, previous two videos didn't make sense, watch this one and then go back to those previous two videos in this same unit. All right? All right, fantastic. So let's move on with this problem. We're going to determine the delta G naught for the following reaction and then determine the temperature shift given the following thermodynamic values at 25 degrees Celsius. So I have this following thermodynamic values which I've extracted from the appendix of my textbook, or the CRC, the Handbook of Chemistry and Physics. This is the equation here. It's a balanced equation. I got 2 moles of ferric oxide in the solid state plus 3 moles of carbon in the solid state, that's the graphite form, producing 4 moles of iron in the solid state and 3 moles of carbon dioxide in the gaseous state. So a few things that you should take a look at about this is that on the reactant side there's no gas. On the product side there's gas. Not just gas, but 3 moles of gas. So on the reactant side there is 0 moles of gas. On the product side there are 3 moles of gas. That means that you should understand that this has more disorder. Think about that, and in terms of the entropy term of which you would expect to get. The other thing that I'm going to note here, which I've previously noted in other videos, is that you have 2 elements in their standard state, okay? And that is carbon, solid, graphite form, and iron, solid. That is, carbon is at 25 degrees Celsius and 1 atmosphere. It is in the solid state as a graphite, and therefore the enthalpy and the Gibbs Free Energy values for the data table are 0. Furthermore, iron at 1 atmosphere and 25 degrees Celsius is a solid. It's iron, like a piece of iron bar. Okay, and that would also have the enthalpy, that's the delta H, and the Gibbs Free Energy delta G as 0 values, as you can see in that data table right there. All right, so there are 2 different methods of solving for the Gibbs Free Energy. We're going to do both of them, just like what we've done in the previous 2 problems, in fact. Okay, one of them is using delta G naught delta G naught for the reaction is equal to the sum of the delta G naught of formation at standard conditions for the products minus the sum of delta G naught of formation at standard conditions for the reactants. The other method is using the delta G naught for the reaction is equal to delta H, that's the enthalpy, minus the temperature times the delta S, which is the entropy. So both of these methods should give me the same or a very similar close value. Okay, we're going to do the first one here, and is delta G naught for the reaction. I got 4 moles of iron, that's times 0, obviously, and 3 moles of carbon dioxide, that's times the negative 394.4 kilojoules per mole, minus the quantity of 2 moles of the ferric oxide, and its value of negative 741.0 kilojoules per mole, plus 3 moles of carbon, and that's times 0, of course. Those 2 elements in their standard state, that's 0. So I really have the carbon dioxide and the ferric oxide to worry about. That's going to give us this value here at 298.8 kilojoules. All right, think about the sign of that number, and I'm going to come back to that being spontaneous or non-spontaneous based on the sign of the Gibbs Free Energy. Now let's do the other calculation. So we're going to do the enthalpy term first. That's 4 moles of the iron times 0, its value of the enthalpy, because it's an element in its standard state, plus 3 moles of carbon dioxide, that's negative 393.5 kilojoules per mole, minus the quantity of 2 moles of ferric oxide, that's negative 822.2 kilojoules per mole, plus the 3 moles of the carbon, and that's times 0. That is an element in its standard state. That gives me a value here that is 463.9 kilojoules. Now again, I want you to think about the sign of that number, and is this endo or exothermic? Is this reactant or product favored? All right, I'm going to come back to that. The entropy term, the change in entropy, is the 4 moles of the iron times its value of 27.2 joules per Kelvin mole, plus the 3 moles of carbon dioxide at 213.6 joules per Kelvin per mole, minus the quantity of 2 moles of ferric oxide times its value of 90.0 joules per Kelvin mole, plus the 3 moles of carbon in its solid state times 5.69 joules per Kelvin mole, and that's its value. Okay, we're going to get a numeric value for this. That's 552.5 joules per Kelvin. Now, I want you to look at the sign of that and think about, is this more ordered or more disordered based on that sign? Is this reactant or product favored? Okay. Now what we're going to do is plug the enthalpy and the entropy terms into the Gibbs free energy equation. The delta G equals delta H minus T delta S. And here is that right here. Okay. And I have done a little bit of unit conversion for you just to make sure that you understand this. The delta S term in the yellow there was 552.5 joules per Kelvin, and I needed to convert that into kilojoules. So I'm dividing this by 1,000, and that's why that's in there. I'm assuming you can do that by now. I'm going to get this value of 299.3 kilojoules. You should see that these two values are really similar, okay, if not the same. They are very, very similar. Now, I'm going to ask myself, is this reactant or product favored? Is this spontaneous? Is this non-spontaneous? All that kind of stuff. So since these two values are positives for the Gibbs free energy, that lets us know that this reaction is non-spontaneous because it's positive. Okay, and what is driving this? Well, look at the enthalpy term. That's the delta H term. It's positive, meaning that it is endothermic and reactant favored. That is going with the non-spontaneous reaction. So that is enthalpy driven. And just to verify this, let's take a look at the delta S. That is the entropy term. It is positive and is more disordered. Okay, and that is product favored. And so that is countering the enthalpy term. And you should have predicted this based on 0 moles of gas on the reactant side and 3 moles of gas on the product side. Now we have some more information that we need to do on this problem still. So we've answered the question of what is the delta G for the reaction. Okay, but what we really need to do is determine the temperature shift. Okay, we do understand that since this Gibbs free energy calculation, either calculation, is positive, it is non-spontaneous. So I need to figure out what the shift is going from non-spontaneous to spontaneous. At what temperature does this occur? Okay, so this is a non-spontaneous reaction because Gibbs free energy is positive, and it is enthalpy driven because the delta H term is positive and endothermic, that's reactant favored, and that is going in the same direction as the Gibbs free energy, which is reactant favored non-spontaneous, which is countering the entropy term, which is positive and more disordered as the more moles of gas on the product side. Again, just a note to yourself, when the enthalpy delta H and the entropy delta S are both of the same sign, you should know that you cannot predict the Gibbs free energy unless you do a mathematical calculation, because they are countering each other. They are going in opposite directions from each other. Okay, so we still have more to answer on this problem here. At what temperature does the reaction shift from being non-spontaneous, that is reactant favored, and a positive Gibbs free energy value, to spontaneous and product favored and negative Gibbs free energy value? So the key to solving this is to this understanding of when the shift goes from non-spontaneous to spontaneous. Okay, and this shift is at equilibrium. And that position at equilibrium is when the Gibbs free energy value is equal to 0. So I have this equation right here. Okay, we've used this multiple times. When is the Gibbs Free Energy value 0, and that's at the equilibrium? Well, that is going to be replaced by that Gibbs Free Energy value. So we're going to replace Gibbs Free Energy, which is the delta G term, and substitute in 0 in for that. Okay, and then what we're going to do is we're going to solve for the temperature. So we got 0 because Gibbs Free Energy is 0. We're assuming this because this is when the shift occurs from non-spontaneous to spontaneous, or spontaneous to non-spontaneous. But this particular problem is going from non-spontaneous to spontaneous. So what we're going to do is solve for the T. So we're going to subtract delta H from this. Then we're going to divide by negative delta S. The negative terms cancel out, and I'm going to have T is equal to delta H divided by delta S. So I'm going to plug in the values from the previous slide here, okay, and that's what I've done here. I'm going to make sure that my units are in the kilojoules form so that they cancel out. So the delta H, or the enthalpy term, is 463.9 kilojoules. The delta S term is 0.5525 kilojoules per Kelvin. Okay, and then I'm going to do the division and then get a value here, and that value is 839.6 Kelvin. So what temperature does this reaction shift from being non-spontaneous to spontaneous? That temperature shift is 839.6 Kelvin. Okay, and this is, if on the previous videos, if you've watched them, or you probably need to rewatch those previous videos and look at the graphic that I had before. This is very similar to those two videos. And I am solving for T star in this case here. I've done that twice before, but this one is just focusing on solving for that value. I can't emphasize enough how important it is to look at the values in those thermodynamic values. Now, it's real all and fine and good just calculating the delta G from the values in the appendix and getting whether or not the reaction is spontaneous or non-spontaneous. But you really can't understand if the reaction is enthalpy or entropy driven without having calculated the enthalpy and the entropy term. Neither can you calculate the temperature of where the shift occurs from being spontaneous to non-spontaneous. So that's why the enthalpy and the entropy terms are so crucial in understanding and in calculating, okay, Gibbs Free Energy. I hope you really enjoyed that crazy video here. And of course, we're going to end with a crazy hat. And I got this hat because I am the wizard of chemistry. And I've had this hat for a long time. I got this at Disneyland many, many years ago. Okay, give me a thumbs up if you like that video. Please subscribe to my YouTube channel. You greatly enhance everything when you subscribe to my YouTube channel. Go to my website. You might be able to get yourself a sticker and maybe a t-shirt. And what is my website with all my videos organized for you? It's right there. Okay? Have a fantastic day. I'll see you next time. Bye for now.